Hello. So I had somebody ask me about some problems with complex numbers and with trying to solve for different roots, thinking of them as complex numbers. So, first situation that we asked about was looking at z to the fourth minus 1 equals 0. And one way to approach this is to think of this as the difference of two squares. Z squared is z to the fourth, and 1 squared is 1. So you can factor it to be z squared minus 1 and z squared plus 1. And then you notice z squared minus 1 follows the exact same pattern, z minus 1 and z plus 1. The second piece is also a difference of two squares in a somewhat less obvious way. Let me rewrite it before I factorize it. Z squared minus negative 1. And if I write it like that, you might be able to follow the same pattern. The first two factors, I'm just going to copy down again. The square root of z squared is z. We already talked about that. And then all you need to think about is what is the square root of negative 1? Well, the square root of negative 1 is I, and you can also consider minus I there. And so then that tells me the four different roots to the original equation are z equals 1, z equals negative 1, because remember that the root is the number that would plug in to make the parentheses equal 0. And so 1 minus 1, negative 1 plus 1. Z equals I, because I minus I makes 0. And z equals negative I. Okay, so this worked out quite nicely because we had the difference of two squares that we could work with there. And because we were able to easily see what the square roots of 1 are. It becomes a little bit trickier if we have a situation with a higher power. So for example, if we had z to the 8th minus 1 equals 0, we could split that up like this, z to the 4th minus 1 and z to the 4th plus 1, but it just gets a little harder to split it up after that point. Let's see kind of how far I can get, and then we'll talk about a different strategy. We know how this one works. This one worked to give us the four roots of positive or negative 1, a positive or negative I, because of everything I just did on the left side of the screen. This other piece, we could continue to split it up like this. We could split it up as z squared minus, what are the square roots of negative 1? Because remember, this is the same as minus negative 1. So square roots of negative 1 are I, and then z squared plus I. But then we have another situation where we would need to split this up even more to be like z minus root I, z plus root I. Then this is minus negative I. So we have z minus the square root of negative I and z plus the square root of negative I. So that gets a little tricky because it's not obvious what the square root of I is. Okay? So if I can approach z to the 8th minus 1 in a different way, then I will also know what the square roots of I are. And so here's the other piece to complex numbers. One way to think about complex numbers is as Cartesian points, x comma y, the real part, comma the imaginary part. The other way to think of them is as a polar system. In other words, r and theta. How far is it from the origin? That's what r stands for. And what's the angle that you need to rotate to get to that bearing? That's theta. And so what we're going to do is we're going to set z to the 8th equals 1, and we're going to treat the letter z as r e to the I theta. R is strictly a real number, and theta is the angle measured the way things are measured on the unit circle. So z to the 8th becomes r e to the I theta raised to the 8th, which is the same as r to the 8th e to the I 8 theta. And so if that equals 1, then I can conclude that r has to equal 1. I'm going to make r a strictly positive number because it's a distance from the origin. If you wanted to make r a negative 1 also, that works okay. It just would rotate your theta by 180 degrees. That's okay. Now, if I think about the number 1 on the unit circle, The number 1 can be thought of as a vector going one step to the right, so it has a r value of 1 and it has a theta value of 0. And so what that means is my theta here, let me try to indicate it a little easier. My theta right over here has to equal 0 after it gets multiplied by 8. And so there are actually a lot of different possible answers for that theta, because my theta could equal 0, or my theta could equal 2 pi or 4 pi, etc. What I'm saying is that I can always rotate a full circle and end up again at the complex number 1. The complex number 1 does not have a unique angle. It has an infinite number of angles that you can do full rotations to get back to. And so that's what I do to figure out my roots of 1, is I just say that 8 theta is equal to 0, 8 theta is equal to 2 pi, 8 theta is equal to 4 pi, etc. So let's see what happens when we do that. I'm going to clear a little bit of space over here on the left side, and then you're going to see how these ideas come together in a pretty nice way. Just the eraser is always a little slow here. Okay, so let's make 8 theta equals 0. So if 8 theta equals 0, then that implies theta equals 0, and that implies z equals 1. Remember that I have an r value of 1, and I have a theta value here in this one of 0. And so that would be z equals 1. And guess what? That's this root that we found over there. If I make 8 theta equal the next value, which was 2 pi, divide by 8. So theta is pi over 4. At pi over 4, you have square root of 2 over 2 and square root of 2 over 2i. Maybe I'll write it down one line. Square root of 2 over 2 plus square root of 2 over 2i. That is at a 45-degree angle, so I'll put that down here on my triangle. So this was the first, on my circle I mean, there's the first z value, there's the second z value. So this is z1, this is z2. The third z value is when your theta is equal to 4 pi, dividing by 8 means theta is pi over 2. A pi over 2 angle is due north, and so that's I. This right here is your z3. So I hope you can see how, as we continue along, each of our values is going to rotate by 2 pi over 8. In other words, by pi over 4. So there's z4. z5 is the number -1. z6 is the number down there in the third quadrant. z7 is there, -i, and then z8 is down there in the right corner, quadrant 4. And z9 is the same as z1. I could have labeled them differently. A lot of times I do. I just kind of messed up. I usually label z0 as the number 1, but this time I labeled that as number 1, so it's okay. Okay, so when I look at this here, I can see that z1 is the number 1, z3 is the number I, z5 is the number -1, and z7 is the number -i. So those 4 roots of the original problem, z to the 4th minus 1, those 4 roots are the odd z solutions that I found here. And all of the even z solutions are at these 45-degree angles right there. And you can also see that when any of them gets multiplied by itself, it rotates by that amount. So what we figured out is that the square root of I is going to equal z2, square root of 2 over 2, plus square root of 2 over 2i. And similarly, the square root of -i is equal to z8 there. So found all 8 of the solutions just by using some trigonometry and then re-express those as Cartesian. All right, let me know if you got any questions. Thanks for watching.